Welcome back to switching AC with Triacs and zero crossing Triac output optocouplers. Literally a handful. Of course, I will go in all the dirty details, but I have also a real world example, and that is switching these nice Chinese heating plates. These come nowadays also with a CE label. Who believes that? Anyway, I have a video about these somewhere, or several, card link to at least one. And yeah, let's start. But before we start, the obligatory warning: I'm working here with mains AC voltage, which can cause serious injury or death. So don't try to replicate what's shown here in the video unless you are qualified. What are our requirements? We want to switch a load that is connected to a AC source. Could be mains AC, but is not necessarily mains AC. Could be any old AC source, for example, low voltage winding of a transformer. And we want to control that switch, for example, with a microcontroller or any other low voltage device here. Could be maybe a battery and another secondary switch. So, requirement 1. We want to have full isolation between the AC side and the usually low voltage side here with our microcontroller and such. Requirement 2. We want to close that switch only when we are zero crossing the sine wave of the AC. Yeah, like I've drawn it here. Switches on here, it switches on here. Always when we are crossing the zero lines. Why do we want to do that? Because if we don't, and for example switch on here at a peak, we create a huge current spike through our load. And that in turn causes a lot of interference and noise and all the stuff we don't want. Side note, only small exclamation mark, I will talk about resistive loads here, okay? It should also work with inductive loads, with capacitive loads. You have to be a little bit careful. There are many ways to skin that specific cat. Obviously not a relay. A relay would make it hard to implement that zero crossing, because a relay is relatively slow. You could buy a solid state relay that implements zero crossing, or you go into using here full bridge rectifier and MOSFETs, or no rectifier and multiple MOSFETs, and But a very simple solution with only 2 active parts is using an optocoupler that realizes the zero crossing part and the isolation part, and using a Triac that switches the AC. And that's what we are going for here. And here I have some Triac output zero crossing optocouplers or photocouplers, and some Triacs, of course, which we will use to switch such a heating plate. I've used especially that type of Triac before in a 2-part tutorial about Triacs, card link. I will not go into basic explanation what a Triac is and does and how to use it in that video. I assume you know already. If not, you can watch at least part 1 of this 2-parter tutorial. On page 7 of the optocoupler, and I'm using an MOC 3063, you find a basic driver circuit diagram. That diagram contains everything you need to build such a circuit. Yeah, you have here the math to calculate your series resistor for the LED. You have here the math to calculate the series resistor for the Triac gate. And well, if you use a microcontroller, you won't need that driver transistor here. A pin of a microcontroller usually can drive a single LED. That's it. See you next time. Bye. Okay, maybe things are not that easy. Here we have the circuit from the datasheet in more detail. Well, basically bigger. And yeah, our resistor for the LED, and I said we don't need that driver in my example because our microcontroller can provide enough current to drive that LCD. The optocoupler, the gate resistor for our Triac, and our load and AC source added just to be complete. The switch from our initial picture basically consists now of that area here, that is Triac, gate resistor, optocoupler and the LED resistor. And please note, this is really just a basic circuit for driving resistive loads in a more or less noise-free, non-industrial environment. In an industrial environment where we have noise and strong magnetic fields, you would have an additional resistor from gate to terminal 1 to prevent any induced currents going into the gate and triggering your Triac. You would also have, when you drive non-resistive loads, for example an RC snubber network across here, and you might have just a capacitor here for absorbing noise, and you might have, when driving capacitive loads, an inductivity here in line with the load. As far as variations of this basic circuit go, it doesn't matter if you place the LED resistor here on the positive side or on the ground side. You can place the gate resistor here at the gate or up here. You can place the load here or here. Do not place the load here. This will blow up your Triac because the Triac circuit is relying on the fact that when it's switched on, you have that voltage drop across the load that will basically collapse your voltage across here and thereby immediately quench your gate current when the Triac is turned on. In the following, we will answer the following questions. More trivial, what value do we need for this resistor here for the LED? What value and what voltage rating do we need for that resistor to the Triac gate? And what thermal resistance should the heatsink have for the Triac? Triacs are not lossless switches. I will use the following parameters for my calculations. So my LED voltage, drive voltage, will be 5 volts, from an Arduino. And my maximum worst case RMS current through the load will be 5.8 amps. And my worst case peak voltage on my mains AC is 358 volts. That's basically, here in Europe, 230 volts effective plus, worst case 10% times square root of 2, peak voltage from RMS voltage. Let's start with the gate resistor because that's clearly more interesting than the series resistor for the LED. And it's the math is too small here, but basically they give you in the optocoupler datasheet this formula. So your resistor should be your maximum peak voltage, P max, divided by ITSM. And ITSM comes also from this data sheet. And that's the peak repetitive surge current that optocoupler can actually switch on its Triac output stage. And in our case, it's 1 amp. But wait, the datasheet of the optocoupler gave us a formula to calculate that resistor here to limit the current here on maximum peak voltage here through the output stage of the optocoupler, that is that tiny Triac here. But the Triac itself we use for switching the mains AC has also current limits on its gate. And that we find, of course, in the datasheet of the Triac under limiting values. There is a IGM peak gate current and it's 2 amps. Yeah, we would have been safe, but better safe than sorry. Now we have everything to do our calculations. So our repetitive peak current from our optocoupler ITSM is 1 amps. Our repetitive maximum gate current for our peak gate current for our Triac is 2 amps. Our maximum peak voltage is 358 volts. This will be important later on. So if we extend that formula, it's really the gate resistor is our maximum peak voltage divided by the minimum of the maximum optocoupler current and the gate current of the Triac. That is 358 volts divided by minimum 1 amp, 2 amp gives us 358 ohms. Add or divided by 0.95, so add 5% tolerance to err on the safe side, using E24 series resistor, we get to 377 ohms, and the next bigger value in the E24 series would be a 390 ohms resistor. But remember, voltage rating. And we would need to use a 2 watt resistor to reach a voltage rating good for 358 volts. Worst case maximum. Your usual quarter watt resistor has a voltage rating of 350 volts. Okay, so good enough for China when in fact here in Europe your worst case voltage is 358 volts. Maybe good enough for Australia, I don't know. Not good enough for here in Germany. So you would actually need to use a 2 watt resistor to reach that voltage rating. At least I don't know of any smaller resistors that have a voltage rating appropriate for that voltage. 2 watts come usually, or some of them come with a 500 volt rating. However, this would be a total waste because we will never dissipate 2 watts here. We are basically dissipating nothing. And just, this is not an exact calculation here, but say our maximum power dissipation is I squared times R, and I assume R is 400 ohms just to make it simpler, and I squared is 1 ampere squared. Our maximum current. That gives us 400 watt maximum power. But the RMS power is much, much smaller because Triacs switch on very fast. And as soon as the Triac is switched on, all the voltage is dropped here, or the majority of the voltage is dropped here across the load. So we have no longer any voltage here, so nothing can flow through that resistor into the gate. So in fact, the switch on time for that Triac TGT is 2 microseconds. And we need to switch that for every half wave of our sine curve, and one half wave takes 10 milliseconds. So we have 400 watts times 2 microseconds divided by 10 milliseconds to get our RMS power, and that is only 80 watts. So what do? Well, you could use a 2-watt resistor if you insist on using only one part, or we take two 200 ohms, run-of-the-mill 5% quarter-watt resistors and be fine and cheaper. These 2-watt resistors cost probably 10 times what a standard quarter-watt resistor costs. So that was a lot of calculations for just one single resistor, but believe me, it's necessary. So we end up with 2 times 200 ohms plus minus 5% quarter watt. You could use other resistors as well with another tolerance and even smaller power rating, and we answered the questions about value, voltage rating, and in addition the power rating. Let's move on to the R-LED resistor. The formula is R-LED equals V-LED. That's a little bit unusual, but I used V-LED here in the circuit diagram, so I stay with V-LED. Minus V forward at I forward, forward voltage at a specific forward current of the LED divided by I forward. And we have to set these 4 parameters for our calculations. And you see I have here a maximum value pair and a minimum value pair. So let's go into the data sheet and look those up. On the absolute maximum ratings, we get an absolute maximum forward current of 50 milliamps, but that was not the maximum forward current I was talking about. We also find somewhere the forward voltage of typical 1.2 or maximum 1.4 volts at 20 milliamps forward current. We are also not interested in that. What we are interested in for our minimum forward current we have to supply is the LED trigger current. That is the current required to latch that triac. And this is for my type, and that's the reason I choose the MOC363 and not one of the other type. It's just 5 milliamps. To get our forward voltage, we have to look into that diagram, forward current versus forward voltage. And at the 5 milliamp line, our maximum forward voltage is a wee bit less than 1.2 volts. Let's stay with 1.2 volts. Don't be too critical about it. And for my maximum forward current, and this I select by looking at the output pins of my MCU, I go for 10 milliamps. And there the minimum forward voltage is, let's say, 1.1 volt. 1 volt. Now I have all my parameters. The maximum forward current 10 milliamps, and that's given by the source of the current, so the MCU output pin, and the limit of the optocoupler is 50 milliamps. We looked at that absolute maximum rating. And the minimum forward current at which the optocoupler actually latches, that is switches on, that's 5 milliamps for my type. And we looked up the forward voltage at the maximum current, 10 milliamps, which is minimum 1.0 volt. And the forward voltage for the minimum 5 milliamp current, which is at max 1.2 volts. Yeah, it looks like these things are reversed, but you have to take into consideration that we have here in that graphics, and yeah, I do zoom down, we have this temperature band, and we want to be in a safe operating condition over the whole temperature band, and that temperature band is 0.2 volts. Putting these values into our formula yields us two resistor values. A maximum resistor value for our minimum forward current and a minimum resistor value for our maximum forward current. I won't read out all the numbers, but just the formula yields us 760 ohms maximum and 400 ohms minimum. Yeah, you know that already. Do the tolerance gain. We are at 724 ohms, respectively 421 ohms. Put that into the E24 series of resistors, 5% tolerance resistors, and we get max value of 680 ohms and min value of 430 ohms. And now I have to make a decision. And I decided to go with the lowest possible resistor value. So we give that little LED here a little bit more current than it really needs. Yeah, but then we're on the safe side that we are really triggering the Triac and the optocoupler. Okay, let's move on to the heatsink calculation for our Triac. Just as a reminder, worst case, we will be switching about 1.5 kilowatt. And that's the formula to calculate the maximum thermal resistance RTH of our heatsink. And it's the temperature differential we can work with. So the maximum allowable temperature of the mounting base of the Triac, yeah, the metal back, minus the ambient air temperature maximum, and that divided by the power we are dissipating in the Triac. And yeah, I already decided on a maximum air temperature, yeah, inside a case, yeah, maybe some ventilation but no active ventilation, of 50 degrees Celsius. Now we have to look into the datasheet of the Triac. And remember, our maximum design RMS current was 5.8 amps. In that set datasheet, we find this diagram here, which gives us for a given RMS current the power loss in the Triac and its maximum mounting base temperature. And we have different curves, and the top curve, alpha equals 180 degrees, is for the Triac being switched on always for the full sine half wave. Okay, that's what we need. So I can't really say 5.8 amps here, but yeah, 5.75, close enough. That leads us to this point. So we have 7.5 watts to dissipate, and our maximum mounting base temperature is 116 degrees. We found our values. Maximum mounting base temperature 116 degrees Celsius. Air, yeah, we already said that, 50 degrees Celsius, and our power dissipation 7.5 watts. Put that into the formula and we get out 8.8 Kelvin per watts maximum for the heatsink. And somehow I doubt that that little heatsink can do that. So yeah, let me find one that does the job, and then we build the circuit and test it. There's a whole lot here on the bench, and there's more over here and down here. So my power supply here and that multimeter, that's my microcontroller unit providing 5 volts here. And this buggers off to my opto-isolator. Then I have an isolation transformer here supplying my whole circuit with 230 volts AC, but isolated from main earth, not reference to main earth, allowing me to probe inside the circuit with an oscilloscope. And the oscilloscope is showing the voltage across our load, which comes next here. And here's our load. I just connected one heating plate because, yeah, for demonstration purposes, it should be enough. And down here is our little circuit. Let's take a close-up. Here are the two leads from our microcontroller, feeding the LED in our little optocoupler here, and our LED resistor, to limit the current through the LED inside here. And that's all for the low voltage side, which is clearly here on the front of this breadboard. The back of the breadboard is all high voltage. And my AC comes in here through the blue lines into one terminal of the Triac inside the optocoupler, and the other side of the Triac is connected via the 2 times 200 ohms to the gate of the Triac. AC in goes also to terminal 2 of the Triac, the middle pin, and then terminal 1, let's say it's not really the output, but the output of the Triac buggers off to my load. Now, let's switch that thing on and see what happens. And I'm really just connecting, my 5 volt line of my optocoupler here to my 5 volt source, and wow, suddenly we have voltage across our load. Let's zoom in there. And you see we have an almost sine wave across our resistive load. The distortions are all from the isolation transformer, which is a big inductivity and does some dark magic here on our nice sine wave. And if I disconnect off screen my 5 volts to the low side of my optocoupler, it's gone. Connecting it again, it's there. And you see the this is a NTC heating element. You see how the voltage at first is a little lower, more load, and then it levels out at a little higher level. That's because it's an NTC heating element, so when it's cold it has a lower resistance, and my isolation transformer is not that good. Now I did a single shot of the switch on process, and you see it really switches on exactly, well, we will see, exactly at the zero crossing of the sine wave. Let's single capture again. And obviously it works perfectly also for the negative half of the sine wave. But let's zoom in on this point a little bit more. And you see it's not exactly switching on at the zero crossing of the sine wave. It switches on a wee bit earlier. So we will have a look into the datasheet of that optocoupler to see what that's all about. And there in a section called zero crossing, we have a parameter called inhibit voltage. And that's typically 5 volts, but it can go up to 20 volts. And the meaning of that is, voltage above which device will not trigger. but the other way around, it will trigger as soon as the voltage across it, positive or negative, it's an AC device, reaches that limit here of, typical 5 volts. That means it's only approximating the zero crossing. It's not switching exactly at the zero crossing. The reason for that being that, of course, our zero crossing circuit here has no independent power supply. It is supplied by the AC across the optocoupler, the hot side. And obviously it doesn't work below 5 volts, okay? So that's the reason why this is only approximating the zero crossing. And that's the reason that even with a zero crossing optocoupler in such a circuit, if you are driving a capacitive load, you need some extra circuitry, because worst case 20 volts across an empty capacitor, it's still a lot of current. What I'm doing now is not switching the optocoupler via my microcontroller unit, but it's supplied 5 volts constantly. Instead, I'm switching the AC and I'm single capturing again. Ooh, what do we see here? Clearly, we didn't switch on the zero crossing, but somewhere in between of the sine wave. Okay, and again, capacitive loads. And the reason being, again, it's not really a zero crossing detection circuit with an independent power supply in there. And well, formally speaking, we do have here a zero crossing, okay? So the thing switches on. And I could capture that a dozen times and I would be able to switch it on exactly at the peak of the sine wave. And that's the reason why our gate resistor is dimensioned for the maximum peak voltage we are expecting in our AC source, okay? Because if that really would only switch on at 0 volts or 5 volts or 20 volts, we could make that much smaller. But in extreme cases like the AC coming on, we might switch here at peak voltage. Finally, some notes on the heat sinking. We calculated a maximum thermal resistance for the heat sink of 8.8 Kelvin per watt. But that includes the contact between the mounting base of the Triac and the heatsink. And you should add at least half a Kelvin per watt for that. Your thermal compound also, it's not 0 kelvins per watt. It has some thermal resistance. So the heatsink itself, the maximum value here is actually 8.3 kelvins per watt. And that heatsink I'm using, actually, that's what I had, is only 3.4 kelvins per watt. So you could basically do with half the size of a heatsink, and it would still run well within limits. And that's it for today. AC switching with down here, zero crossing Triac output optocoupler and a Triac. Until next time, bye.